Hi everyone, my name is Pavitra V, Department of Chemistry. Today we are going to discuss a topic called gas liquid chromatography, that is GLC. First we will see the definition of a chromatography, that is chromatography is a separation technique of a mixtures into individual components using a stationary phase and a mobile phase. Based on the nature of stationary phase and mobile phase, chromatography can be divided into following types: gas-solid chromatography, gas-liquid chromatography, solid-liquid chromatography, that is our column chromatography, thin layer chromatography, and high-performance liquid chromatography. Other than that, liquid-liquid chromatography, paper partition, column partition, etc. These are the types of chromatography. Now we will discuss the gas chromatography principle. Gas chromatography consists of gas-solid and gas-liquid chromatography. Both types, gas is used as a stationary phase. In GSC, that is gas-solid chromatography, principle of separation is adsorption. It is used rarely because of limiting number of stationary phases and increased resolution time. Next one is the gas-liquid chromatography. The principle of separation in GLC is partition method. Here the mobile phase is in gaseous state. Stationary phase is liquid coated onto a solid support. Components to be separated will be converted to vapor and mixed with mobile phase. Component more soluble in stationary phase travels slower, that is eluted last. Component less soluble in the stationary phase travels faster, that is eluted first. No two components have same partition coefficient for fixed combination of stationary phase and mobile phase. Other conditions, hence the chromatographic, this is the chromatographic principle. See, this is the mobile phase movement and this is the stationary phase. This is the equilibrium established at each point ideally. So this is the sample and this is the mixture. The molecules of the mixture interact with the molecules of the mobile phase and the stationary phase. Each molecule interact differently with the mobile phase and stationary phase. The point we have already discussed, the retardation of rate of movement of molecules, that is different distribution coefficients and different net rates of migrations. So this based on the movement of the particles in the mobile phase and stationary phase. Next we have a gas liquid chromatography principle. This runs on the principle of partition. GLC, the components of vaporized samples are fractionated due to partition between a gaseous mobile phase and a liquid stationary phase held in the column. And the next one is the instrumentation of GLC, which consists of a tank of carrier gas and a flow regulator and a flow meter, which regulates the flow of the carrier gas into the column. Next one is the injection port. Injection port is nothing but where the sample is to be introduced into the column, and this is the column. Next one is temperature controlled device. We are controlling a temperature. A definite amount of temperature is supplied to the column or maintained temperature. Next one is the detector. Detector just detects the sample separation. Next one is the microprocessor or the recorder, which record the signals given from the instrumentation. So we will study one by one. This is the apparatus setup. This is the carrier gas cylinder. This is the gas flow regulator, which regulates the flow of carrier gas. This is the sample injector port. We are injecting the sample into the column through this point. And this is the column. The column is kept in the oven. A particular temperature is maintained at the oven. This is the detector. And this is the waste, is nothing but the impurities can be ejected or removed through this channel, and this detector is connected to a computer or a data analyzer, which analyzed in the form of a peak or a graph. So this is the apparatus setup of gas chromatography. We will see one by one. First one is the carrier gas cylinder or a mobile phase. An inert gas such as helium or nitrogen gas is used. Function is to transport sample vapors through the column. There will be no chemical interaction with the sample. Just it carries the sample. Typical parameters, that is column inlet pressure is maintained as 10 to 50 pascals and flow rate is maintained at 25 to 50 ml per minute. This inside the packed column. Precise control of carrier gas flow rate is critical to obtaining reproducible retention times. Next one is the sample injection. Sample is injected using a syringe into a flowing system or a flowing stream of hot mobile phase. High temperature, at least minimum 50 degrees Celsius above the boiling point of the sample is maintained in order to cause vaporization of the sample. That vapors are carried out through a carrier gas. Introduces a narrow plug of sample vapor onto the column, that is the injection port. Various designs have been made for this injection or the sample injector. The packing column injector is 1 to 5 microliter of sample. For capacity of columns, a split valve is used to introduce a small fraction of a sample onto the column. So sample injector looks like this. This is the apparatus setup for the sample injector. This is the syringe and this is the septum. This is the septum purge, that is the distance of the septum, that is moving inlet. This is the syringe needle which is going inside and into the injector. This is the vaporization chamber, zero dead volume connector, and this is the column. Through to the column it is injected. Next one is the columns. Column is a heart of gas chromatography which decides the separation efficiency. It is made up of glass or copper. In order to avoid the corrosion with the copper, we will use sometimes glass. For some reactions, there will be a glass cannot be withstand to a temperature, higher temperature. For that cases, we will be using this copper columns. So columns are of two types. One is analytical column and another one is the preparative column. The analytical column actually a separation taking place. The length is 1 to 2 meters, outer diameter 3 to 6 millimeter. Next one is the preparative column. The length should be 3 to 6 meters, outer diameter is of 6 to 9 millimeters. It is actually a dimension of analytical column and a preparative column. Next one is the column oven. Column is kept inside a oven. Precise control of a column temperature. Column temperature should be slightly below the boiling points of the solutes but above the dew point, or that is no condensation reaction is taking place at that temperature. For complex mixtures with a broad range of boiling points, use programmed temperature. We will see what is this programmed temperature in a further slide. So the precise control of a oven temperature is critical to obtaining reproducible retention times. So the retention time depends on this. Next one is the detectors. Generate an electrical signals proportional to solute concentration or the mass flow rate. So ideal characteristics of a detector is it should be high sensitivity. It should sense the impurities and the separations very precisely and accurately. Rapid response time. So the results we will get in a less consumption of time. Non-destructive technique. Applicable to wide range of samples, easy to use, stable and predictable responses. So detectors should have these ideal characteristics, and then we have so many types of detectors. In that we will discuss thermal conductivity detector. Element is electrically heated at constant power. Temperature depends on thermal conductivity of surrounding gas. So this is the apparatus setup for a thermal conductivity detector, in which it measures the conductivity with respect to the reference. When an analyte comes off filament, temperature goes up, resistance goes down. As the temperature increases, the resistance decreases, so that the electrical conductivity is more. By that, we will calculate the temperature change. So the mechanism of that detector is, the detector cell contains a heated filament with an applied current. As carrier gas containing solutes passes through the cell, change in a filament occurs. That is, current change occurs. The current change is compared against current in reference cell. So by referring a standard one, we are giving an actual result. This is the sensitivity range and the selectivity, gases, and the temperatures used. Next one is the recorder. Recorder is a device that draws the chromatogram, or which gives the results and recorded in a recorder. Next one is the factors affecting the separation. Particle size and surface area. Based on the particle size, the factor, that is the elution capacity, will alter. Carrier gas flow rate, type and amount of stationary phase, column length, column diameter, and the column temperature. These are the factors which affects the separation of mixture. Next one is the temperature programming. This is very important. In gas chromatography, we are usually using this temperature programming, which is capable of performing based on the temperature gradient, is known as temperature programming of gas chromatography. This TPGC is a very important procedure which is used for attainment of excellent looking chromatograms in a least time possible. Chromatograms is nothing but chromatographic results in a graphical representation. Isothermal, that is at the same temperature, keep oven at one temperature throughout the run. Not very useful. So throughout the process we are not maintaining a same temperature. Based on the different amounts of, or based on the different kinds of molecules, we are just altering the types of temperature. So this gradient temperature profile, for example, 40 degree holds for 10 minutes, then 10 degree rise per minute to 240 degree, and hold there for 20 minutes. Advantage of 1 resolution and 2 analysis time. So that is nothing but, see, when we compare the graph, see, when we are considering the 60 degrees Celsius, this is the graph obtained at 60 degrees Celsius. For every 2 minutes, we are rising the temperature 5 degrees Celsius. Okay, 5 degrees Celsius rise per minute. This is the run time 24 minutes. This is the elution temperature, that is 173.2 degree Celsius. So you can see the resolution of the spectrum. When the same experiment is carried out when a 10 degree rise per minute, then the run time is 15 minutes. The elution temperature is 192.7 degrees Celsius. Here the resolution is little bit less when compared to the first graph. Next one is the same procedure is carried out when there is a rise in 15 degrees Celsius per minute. The running time is decreasing still 12 minutes and the elution temperature is 211.4 degrees Celsius. So this is the temperature programming. By altering the temperature 5 degrees Celsius per minute, we are getting a high resoluted spectrum that is very easy to analyze. So that one is explained. This is the advantage: high resolution of lighter components, sharp peaks, reduced run times, lesser carryover, high sample through output, and the extended application range from the single column. So this is the advantage of temperature programming in gas chromatography. Next one is the advantages of GLC, both qualitative and quantitative